Welcome, everybody. I'm Livneh Duncan with Western Water Assessment at the University of Colorado Boulder. Thank you for joining us today. We're really excited to see so many of you here. In today's webinar, Dr. Noah Molotch and Dr. Ben Livneh will be discussing the impacts of climate change on snowpack and streamflow in the Western US. And let's see if I can advance my slide. There we go. Before we get started, I wanted to share a bit about Western Water Assessment for those of you who haven't worked with us before. We are an applied research program that works to address societal vulnerabilities to climate variability and climate change, especially those that are related to water resources. As the map shows, we are based in Boulder and Salt Lake City, but we work across the Intermountain West, which includes Colorado, Utah, and Wyoming. We're also one of 11 teams in the NOAA RESA program, and that stands for Regional Integrated Sciences and Assessments. Our speakers today are Dr. Noah Molotch and Dr. Ben Livneh, who are both Western Water Assessment Principal Investigators and professors at CU Boulder. Noah Molotch will present his research mapping snow water equivalent in real time using satellite data, models, and ground stations, while drawing on collaborations with water resource stakeholders from across the Western US. Then Ben Livneh will examine snow drought in the Colorado River Basin over the past century, and will evaluate the importance of how snow drought is defined, its historical variability, and its role in modulating streamflow. He will also summarize recently completed work that examines the impact of anomalously low snowpack on streamflow prediction across the West, and discuss ongoing efforts that explore new tools in seasonal water supply prediction. The presentations are going to be recorded, and all totaled will last about 45 minutes, and then we'll have time for a Q&A period. So please feel free to submit questions via that Q&A button. You should see that window in your Zoom menu. And we will be sure to share a link to the recording of this webinar afterwards. So with that, I'm going to hand it off to Noah. So let's see if I can stop sharing my screen. There we go. Take it away, Noah.
Great. Thanks very much, Livneh, and thanks everyone for making it to this webinar. I have the challenge of presenting this information to a variety of audience members here with different backgrounds, but my hope is to strike a balance between presenting to you some recent indicators that snowpack is changing associated with climate change, and then give you an introduction to how we're providing information to help the water management community deal with those changes. And that's primarily through the generation of spatial snowpack information from distributed models, from ground-based data, from satellite data, and in some cases from airborne data. A lot of collaborators on the team for this work. Their names are listed here. They include Leanne Lestak, Kuhan Yang, Keith Musselman, Keith Jennings, and lab group alumni Taylor Winchell and collaborator Ben Livneh. So many of you are familiar with the concept that the snowpack has been changing as in the Western United States as the climate has warmed, and probably the most common view graph for illustrating that change is shown here on this slide. And I like to present this in the context of how things have changed over the past couple of decades, because if you look at the trends in April 1st snow water equivalent from the years 1950 to 2000, that's what's shown on the left here, where the red circles are decreases in SWE and the blue circles are increases in SWE. And these data were pulled together by Phil Mote and his collaborators, and they updated these to data up to 2016, which is shown on the right. And I think it's actually powerful to look at these together, because what you see is that the red circles, which are those declines in SWE, are far more widespread when we look at the data up through 2016. And the magnitude of the trends maxed out at around 60% when looked at up to the year 2000. And now you see the scale has to be increased to 80%. If you look at the largest red circles here, those are for 80% declines in snow water equivalent for this period up through 2016. So there's been some dramatic change in snowpack water storage across the Western US, and most of you are familiar with that concept. Now, a couple of reasons for these trends. One relates to the fact that we've been experiencing proportionally more rainfall and less snowfall. So Keith Jennings and my team led this work that showed the spatial distribution across the northern hemisphere of the temperature threshold at which precipitation shifts between rainfall and snowfall. And kind of the point to take home from this is that snowfall doesn't occur at the same temperature threshold everywhere across North America's land surface, and really the northern hemisphere in general. And so when you look at North America and kind of zooming in on the United States, what you can see is that in more maritime regions, we actually see shifts in precipitation from snowfall to rainfall at relatively low temperatures. And it takes a larger amount of warming to shift snowfall to rainfall in more continental environments. And the mechanism behind that is primarily associated, we believe, with latent cooling of hydrometeors in the atmosphere, which allow precipitation to stay in the form of snow at relatively warm temperatures. But nevertheless, there's a climate signal that we can look at to see how our precipitation has been shifting from snowfall to rainfall. Another important piece of work that we've concluded recently, this led by Keith Musselman and other members of the research team are at NCAR. And what's shown in this view graph is the distribution of SNOTEL stations that have reported increases in wintertime snowmelt over the period of record. So these mostly go back for the past 3 to 4 decades. And if you look over this time period, you can see the red circles indicate those SNOTEL stations that have seen an increase in the frequency of snowmelt before April 1st. And then if you want to look at the trend in the percent of annual melt that is occurring before April 1st in terms of the percentage per decade, that's what's shown on the right, where the darker green circles represent those places that have had the most dramatic increase in wintertime snowmelt or snowmelt before April 1. And so this provides a very useful metric for looking at the climate sensitivity of the snowpack that goes beyond just looking at snow water equivalent, because increases in precipitation, for example, can counteract increases in melt such that you may not see a snow water equivalent decline in a climate signal, whereas there may actually be a signal there associated with snow melt. And so this, as far as we're aware of, is the first paper to document from observations a trend toward increases in snowmelt across Western North America. So when it comes to water management, which is, I think, the focus for this particular webinar, one of the things that drives a lot of my interest in this topic relates to the fact that if we're predicting water supplies based on statistical metrics from point data and the spatial patterns of snowpack are changing, then we should expect that those statistical models will not perform as well in the future. And so this motivates research to bring improved snowpack information in a spatially explicit manner toward those kinds of predictions of stream flow and water supply. So the objective here is to develop more accurate spatial snow estimates, in this case using satellite data, but blended with ground-based information. So the protocol is to develop a reconstructed catalog of snow water equivalent distribution using satellite data and energy balance models across regions of interest. In this case, I'll show data for the state of Colorado. But we have the ability to do this across the Western United States, and we've been doing it in the Sierra Nevada as well. And then we use a multivariate regression model to interpolate in real time snowpack information from SNOTEL and CoCoRa's SWE observations. And that interpolation is based on some topographic metrics, as well as the historical reconstructed snow water equivalent from satellite data. So that's what's unique about the statistical approach, is it's bringing the historical SWE reanalyses into the statistical model. And so we've been able to do this in near real time, generating the snow water equivalent product at 500 meter spatial resolution. And it's available from the year 2000 to present. And I'll show you some real-time data so we can look at what the hydrologic conditions are in Colorado for this particular water year. So a little more explicit description of the methodology here. So if we think about the various independent variables that we can use to interpolate SWE measurements. So in this statistical model, the dependent variable are the SWE measurements on the ground from SNOTEL and CoCoRaHS. And then the independent variables are kind of some of the old hat techniques of using slope, aspect, elevation, and a number of the variables that are included in the PRISM precipitation product. For those of you who are familiar with that product, these include the northwest barrier difference that aim at getting at the orography in the system, the distance to ocean, which at the regional scale can be relevant in the context of snowpack accumulation. But what I really want to emphasize here is that these historical satellite/model derived SWE estimates are the real bread and butter of this statistical model. We have hundreds of spatial SWE patterns that have been reconstructed using our reanalysis approach from the historical past. And those historical patterns can provide a lot of information for interpolating data in real time. So it still relies on some statistical analogs from the past, but in a more spatially explicit way than, say, simply correlating SNOTEL SWE to total stream discharge over the course of the runoff season. So we're bringing this into more of a spatially explicit analog approach. We've performed this work in a variety of regions of the Western United States, as I mentioned before, including over 450 SNOTEL and over 300 CoCoRaHS sites. The SWE reconstruction that provides us with that catalog of analog patterns from the past are documented in a couple of publications here, also exploring the use of other research groups' SWE reconstruction estimates, because others have made improvements to the model that we developed. And then the independent variables that I mentioned before are also included. And this, importantly, is the MODIS-based snow water equivalent reconstruction is an essential independent variable, as I'll show you in a moment. So the quick note on how the reconstruction works, basically by observing when snow disappears, we have a constraint on the duration of the snowmelt season. And so effectively what this model does is runs a snowmelt model backward from the end of that snowmelt season to the beginning of the snowmelt season. And then using calorimetry, we can sum the joules that go into each grid cell across the landscape. And through the latent heat of fusion, we can convert those joules to a mass of water that existed before the snowmelt began. So we're recovering the snow mass at the beginning of the snowmelt season through this calorimetric approach. So it really just relies on the fact that we have relatively good observations of snow-covered area from satellite, so we can see when the snow disappears. And then it relies on an adequate calculation of the snow atmosphere energy exchange to calculate daily, or in this case, hourly snowmelt throughout the snowmelt season. This requires, in order to estimate the snow mass, it requires that you observe the snow disappear. So the model itself is not applicable in a water resource management context because you have to see the snow disappear before you can estimate how much is there. So what we're doing is using the historical reconstructions in our real-time statistical model. So here's what the spatial distribution of snow water equivalent looks like for the Southern Rockies region. So you can see Denver, Albuquerque, and Salt Lake City denoted here. So it's a fairly large area. The upper Colorado River Basin is the outline that's shown in the solid black line. And you can see the variability from year to year, in this case from the year 2000 to 2012, just shown for example, where the pixels in red are those that have below average snow water equivalent, and pixels in blue are those that have above average snow water equivalent. And these historical patterns, which we have actually daily for all these historical years, and now more historical years, these historical patterns can be used as an independent variable in our real-time statistical model. And to give you a sense as to how valuable that is, this gives you an indication of the correlation represented as the R squared between all of our independent variables and the measured snow water equivalent for April 1st between 2010 and 2015 for our upper Colorado River Basin domain. And you can see that the R squared values are quite low. They're arranged in left to right from least important to most important. So you can see slope has very little correlation, in part because snow-tell sites tend to be on relatively flat ground, so no surprise there. But as we move from left to right, you might expect elevation to have a decent correlation with snow water equivalent aspect. The regional slope, which is getting at kind of a broader area, northwest barrier distance, so that gets at the orography. But I want to bring your attention to this one in red, which is the historical reconstructions. Those historical patterns of snow water equivalent are by far the most strongly correlated with the real time, how much is on the ground at a given time. In this case, for April 1, the historical patterns have much higher correlation with the snow water equivalent than any of the topographic metrics. So in our multivariate regression model, we can exploit the information that exists in these historical patterns and all of these topographic metrics to get our best possible estimate of SWE. So here's some example data. We've been doing this, like I said, in near real time. So here's some near real time data. Here's the snow water equivalent distribution for March 29th of 2021. So about a month ago for the state of Colorado. And here is what it looks like for April 18th, so about 12 days ago for the same domain. And so you can see the decline in snow water equivalent. For those, I see people are on the line from all over the country, but we had quite a bit of late spring snowfall this particular year. And so you can see the pretty big decline in snow water equivalent in the lower elevations between the two images. And that's a result of those late spring snowstorms melting during our relatively warmer conditions. In these real-time snow water equivalent reports, we do include percent of averages by pixel. So you can see the areas that are relatively below or above average. So those that are below average are shown in the whites to browns, and the areas that are above average are in the light to dark greens. And then we also include the lumped percent of averages for the major river basins draining out of the area. And so you can see variability in those conditions as of April 18th is pretty dramatic. 64% of average for the South Platte, 70% of average for the White Yampa system, 55% of average for the Upper Arkansas. We also include zoom ins on focus areas. So this work is done in collaboration with Denver Water. So we bring a specific emphasis to the watersheds that are of interest to Denver Water. And those watersheds are shown here. I actually don't include the city of Denver in this map, but it's kind of just right in this general area right here. And you're allowed, by doing this, we're able to kind of inform or provide information for their management decisions in the context of all the watersheds that they have interest in, whether those are direct systems that flow directly into the into the city of Denver, like the South Platte, those that are part of the transbasin diversions that come from the Western Slope, and those that represent paper fill to supply water into the Western Slope system to replace water that's diverted to the Front Range of Colorado. And the percent of averages for these watersheds are shown on the right-hand side. We're also working as closely as possible with the team of the Airborne Snow Observatories, wherever they're flying in an area that we are also working in. We're utilizing their data to explore the structure of errors in our models, and now we're moving in the direction of real-time bias correction of our models with the Airborne Snow Observatory data. We actually can see systematic biases in our models with the ASO data, and because of the systematic nature of those errors, we can actually model those errors and therefore improve our SWE estimates for time periods when we don't have the Airborne Snow Observatory data. So the ASO data has proved to be very useful for us. Jeff Deems provided this snapshot of the Blue River Basin also for April 18th. And they're able to provide volume estimates, give indications of how SWE varies with elevation, which is shown here in the middle, with SWE on the horizontal axis and elevation on the vertical axis, and as a function of aspect, which is shown here on the right. We're also comparing our SWE estimates with variability in SWE as observed or modeled, I should say, from the National Weather Service SNODAS product. And we include in our reports spatial maps of the difference between our product and SNODAS, where the areas in blue here are those where SNODAS is higher than our product, and the areas in red are those where our estimates are higher than SNODAS. We're anxious to extend this to new areas. So for those who are interested, please reach out. I'm running out of time, so I'm going to go a little quicker on this slide than I would like, but just know that we have the capability to do this across the Western United States and look forward to partnering with new folks. So in conclusion, the regression spatial SWE estimates provide valuable information for augmenting point data and the SNODAS product. The products are produced weekly to monthly in collaboration with end users, and the approach can be applied in conjunction with airborne snow measurements in the context of validation and or temporal change analysis. And with that, I'd be happy to turn it back to Benay, who I think will introduce Ben and will take questions at the end.
Exactly. Thank you so much, Noah. This is really fascinating, and it's so cool to see the data for this current water year. So with that, I will turn it over to Ben Livneh, and please, everybody, continue to ask questions using that Q&A button that you should see at the bottom or the top or the side of your screen, depending on which version of Zoom you're doing. And with that, I'll turn it over to Ben. And Ben, you're muted.
Yep, thank you. I think I just figured out how to use Zoom for the first time. That's a joke, but thanks so much. And thanks everybody for tuning in today. I'm going to kind of build off of some of what Noah was talking about from the snow perspective. And I want to think also more about Streamflow and the combination of snow drought and seasonal water supply predictability. So I want to just acknowledge the contributors, Andrew Badger, Aaron Heldmeyer, and Nels Bjark. Right, so snow drought is a term that some of you may have heard, and it's kind of a bit of a newer term, even though the concept has been around for a long time. So I want to talk a little bit about that. The first half or so of what I'm going to talk about is looking at the difference between, say, warm and dry conditions. And then the second half, I want to show you some recently completed work and some new emerging work into essentially the impact of low snowpack on seasonal water supply forecasts. So snow drought. Okay, so very generally, I think we've all seen a picture like this before or have driven through the mountains at some point in the spring. And really, we're talking about low snowpack. Okay, and this has obvious implications for water management, for ecology, for recreation, and many things, right? So one of the first sort of formal definitions of this was given by Adrian Harpold, who actually used to be here at CU and actually was working with NOAA and in his group. And he proposed a distinction between a dry snow drought condition and a warm snow drought condition. And so basically, a dry condition is just a lack of winter precipitation, and a warm condition is a lack of snow accumulation when you have near normal winter precipitation. So you can kind of think about the warm condition as, well, you're getting your rain, your precipitation, but it's not falling as snow, it's falling as rain. So one way to think about this, and we have this new paper my student Aaron Heldmeyer has submitted, and we're trying to put snow drought in the context of more sort of traditional types of drought. So here I've got a triangle where you can see meteorological drought on the top, that's low precipitation generally, and hydrologic drought, which is low surface water, generally low stream flow, right? And I've got this dashed arrow here because I think these connections are like pretty well understood, or at least pretty well studied. Instead, what we're interested in exploring is snow drought, which is a condition of low snowpack. And its connections to meteorological drought include things like reduced snowfall or even rain on snow events. And then the connection to water supply, if you will, is reduced snowmelt or maybe early snowmelt. So that kind of puts this work into context a little bit. And I'm just going to share with you some of the highlights of what we've done here. Okay, so we looked at the upper Colorado River Basin as our study domain, and there's actually like a pretty fine mesh overlaid on this. That's the model grid that we used. I've got this data set that has gridded meteorology and like simulated hydrology. So we use that. We also used SNOTEL information and the Bureau of Reclamation naturalized streamflow. Okay, so what does this look like? So we analyzed the years from 1916 to 2018, so like 103 years, okay? And we first classified snow drought as any year where the snow is below average. So that's an extremely generous definition of a drought, right? It's just below average. But within that, we applied this new classification scheme, which is based on a statistical technique called clustering. And it gives us these three different groups. So we did this on the basis of SWE divided by P, so snow water equivalent divided by precipitation for that year. So that kind of says like how much of the precipitation is falling as snow. So larger values would mean more snow relative to rain. And then the horizontal here is just the total precipitation. And each of these points is for 1 year, right? So what I want to draw your attention to are these, well, first that we proposed not just dry and warm conditions as was done before, but also this combined category of warm and dry snow drought. So I'll just draw your attention to the fact that these warm snow droughts, if you see, they can actually have more than average precipitation, and yet the snowpack, which isn't actually shown here, for anything that's in color is below average. So that means you had more than normal precipitation, but less than normal snow. So that's important. And then you've got dry conditions, and the dry conditions tend to be to the left of this zero line because they have less than normal precipitation, and warm and dry is both. So what does this look like through time? This is a graph of the annual peak SWE anomaly. The colors are the same as in this graph. So you can see the different types of snow drought, okay? And they're all below average because that's part of the definition of snow drought. And then down here is the streamflow anomaly for each year, which I took the Bureau of Reclamation, and we used those data. So what's interesting actually is you can see some of the warm snow drought years actually have above average streamflow. So that's something to keep in mind. And sometimes it's not just the amount, but it's the timing. And we'll look at the timing shortly here. So that gives you a sense of that. What I think is probably the most striking of this is if we look at the snow droughts in the context of elevation. Okay, so here's our domain. And then this is called like a hypsometric curve. A hypsometric curve shows the amount of land area you have at different elevations. Okay, so imagine this map of the Colorado Basin, and you just took the area at each elevation. It would look like this. So you have the most area at low elevations, and as you go up to your mountaintops, you run out of land. So now, if we look at snow drought across elevation, what's I think very interesting is that we see snow drought primarily, warm snow drought is primarily a situation where you have very low snow at low elevations, okay? Whereas up higher, your snow is probably, it's still low, but it's a lot closer to normal. And then if you look at the dry snow drought, you tend to see a more uniform lack of snow. And then warm and dry is kind of a combination of the two. But so because we have low snow at low elevations, and because the low elevations are places where snow probably starts melting earliest in the year, our hypothesis was that, okay, we may end up with actually earlier snow melt and earlier peak runoff. And so we went back to the Reclamation Streamflow data, and we essentially subset it by the type of snow drought. And this is for the entire upper Colorado River Basin above Lee's Ferry. So that's a very large area. We also did this for the sub basins. And generally what you see is that both warm and dry snow drought years have centroid timings, that's the vertical line, that are about a week earlier than the observations, which the non-snow drought years, which is the black vertical line. Whereas the combination warm and dry, the purple line is about 2 weeks earlier on average across 103 years. So I think that probably this is could be one of the more important findings of this work. And so it's currently in review at the Journal of the American Water Resources Association as part of their special issue on Colorado River drought. Okay, so I'm going to kind of shift gears now to talking about what does low snowpack mean for our ability to anticipate drought. And so this is work, I'm going to show you work that was completed last year and published. And then I'm also going to touch upon the ongoing aspect of this and this new project that we have recently started, funded by NOAA. Okay, so our hypothesis is that from the perspective of water management, that as snowpacks decline, they will become less useful in seasonal water supply prediction, because most of you know that snow is one of the most important, like specifically say April 1st snow is one of the most important predictors of seasonal water supply. And so given future projections in warming and some of the directionality that like NOAA was talking about before, we think that our hypothesis is that that will mean that snow will become less important in seasonal water supply prediction. So I don't want to get too bogged down in the details of what we did, but I just kind of want to give you a sense of how we made our estimates of this. So basically, we tried to follow a kind of a seasonal water supply prediction method that more or less resembles what people are doing in practice. So here's an example of 30 years of April 1st snow water equivalent. We chose April 1st because it's among the more common dates, but we also did this for a few other dates. Nevertheless, this is data from the SNOTEL site here near Steamboat Springs, okay, and 30 years. And then the black lines here are the April through July flow for the Yampa River, which is downstream of this snowtail site. And so we basically fit a statistical model, really simple, just as a function of snow. And then when we took the next 5 years and applied our statistical model, and then we could calculate the errors in the model and then attribute those to the changes in snowpack, for example. So we did this out to the year 2100, and we actually used, that requires a model because of course we don't have observations yet for most of those years. And so we used the hydrologically downscaled projections. So we got the VIC model projections from the Bureau of Reclamation, and the climate models are from the CMIP-5. Everything I'm going to show you is based on like a 28-member analysis. So just kind of skipping to many steps, we use something called an equitable threat score, which said like, how often does the physical model say there's a drought? Okay, so the future sort of observation of drought. And then based on that, how often does our statistical model, which is trained on snow and streamflow for 30 years and then's applied for 5 years, how often does that correctly predict that there's drought? And basically, what you see here is that the warmer colors are places where drought prediction on the basis of snow alone is projected to get less skillful, okay? And that's a big fraction as you get out to the end of the century, the 30 years at the end of the century. Decreases in skill are primarily attributed to missed forecasts. So in this sort of threat score context, a missed forecast is when the prediction was for no drought and that for a drought actually to occur. So that's a really important type of error, because that would put a hypothetical water manager in a position that they were not anticipating a drought. So that's really important. And I want to remind everybody that this is just based on predictions using just snowpack alone. Okay. So the other big feature that came out of this is that the changes in drought prediction skill actually have a really strong and statistically significant variation with elevation, right? And so the 4 major river basins of the West, or regions, we get this statistically significant relationship with elevation. So better predictions at higher elevations. And so one of the take-home messages from this, when we were talking with water managers, was we said it would make sense to preferentially use higher elevation observations, or maybe invest in evaluating higher elevation information for that. Okay, so when we decided to now kind of make these a little bit more realistic and even a little bit more experimental, we decided to add other predictors. Okay, so non-snow predictors. Can the future drought prediction skill be recovered when you add new information? So we started with snow water equivalent, and then we also added these new variables: precipitation, which is very commonly used, temperature, which is perhaps less common, and then soil moisture, which is more of a newer kind of concept. And we added these into our predictions, and without fail, it really improved our prospects, such that only about 1/3 of areas in the West see decreased predictive skill during drought, which is down from 83%. The original graph looked like this, so there's a lot more orange and brown in the original versus this one. One thing to keep in mind, because of the importance of high elevation, the upper Colorado River area, actually seem to be in pretty good shape according to this analysis. Most of the skill that gets added actually though is at lower elevations, and this kind of shows just the improvements in skill. And I don't want to belabor this point too much. So that's kind of just a brief sampling of that work. And now I just want to add one more thing, which is about our new project. Actually, One of my co-PIs is Livneh Duncan on this call, and Joe Kasperizak from Civil Engineering here at CU Boulder. And we're looking for input, and we're going to be sending out a survey soon. But basically, our goal is to try to identify alternatives to snow-based streamflow predictions to advance the future of drought predictability. So like, if you are somebody who either uses seasonal streamflow or seasonal water supply forecasts, or also somebody who generates seasonal water supply forecasts, we would love to hear from you, and we'd love to include you in our survey. And then we will use that information in our research, and we'll test different sort of commonly used methods and see which are the most promising, and then we can report back. So hopefully it'll be quite productive. If you do participate, we hope to make it worth your while. So in summary, snow drought in the upper Colorado River Basin can be meaningfully distinguished as either being warm and or dry. And each of those has a unique elevation dependence. Seasonal water supply predictions also seems to have a strong elevation dependence, where higher elevation locations seem to be more resilient, and lower elevations seem to be places where we could really benefit from incorporating new environmental variables. And on that topic, yeah, I mentioned this new research. It would be great to include others. Anybody on this call who wants to be involved who isn't already involved, you could shoot Livneh an email or myself. So I just want to acknowledge funding sources, and thank you very much.
Wonderful. Thank you, Ben. This was really fascinating too. I really appreciate both of your presentations. And so now I think what we can do is transition over to the Q&A period. We still have about 15 minutes left. And so I will go ahead and run through some questions. And in the meantime, please continue to ask questions using that Q&A button. You can also send them through chat, but it's easier for us to lose track of them. So please try to use the Q&A button so that we don't miss anything. I do see one question that I can answer really easily, which is this being recorded and will it be shared soon? Yes, absolutely. We're recording this webinar, and probably early next week, we will have it posted online, and then we'll email all webinar registrants the link. So do not worry there. And so with that, I will ask one, I think a quick, easy question for Noah has come in. The question is, Noah, is the data, so your SWE product data, publicly available on the web?
It is, and I can include a link to that. The data for this year have been provided to the client, which is Denver Water, and so we haven't posted this year's data yet. But historical years are included on the web, and I'll put that in the chat as soon as I have a minute.
Great, thank you. Let's see, okay, so I've got another question here related to spring snowpack declines, and I think it could be applicable to either of you. And that is there research, or has any of your research on spring snowpack changes been correlated with land cover or land management practices? I wonder if either of your work has considered land cover or land management practices, or if you know of other, interesting work related to that.
Well, Ben and I have actually collaborated on this topic, so either one of us could probably give the same answer. You want to go, Ben?
I'll go for it, Noah.
Okay. So Ben and I actually collaborated on a study that looked at land cover change associated with the pine beetle epidemic, and we documented changes in snowmelt runoff associated with loss of forest cover with the mountain pine beetle. But I haven't really been involved in any work that's directly looked at the impact of the land cover disturbance on the snowpack itself. And I think that there are a handful of folks out there in the research community who've looked at this. It's a challenging thing to observe and to constrain all the other factors that might influence snowmelt. But we've done some modeling studies to look into this associated with the mountain pine beetle.
Thank you. Wonderful. Let's see, I've got another question for Ben. Could you comment on the relative predictive value of adding soil moisture information?
Yeah, sure. So in general, it seems like I actually was a part of a study like 10 years ago that looked at this a little bit, and we generally found that those basins that are heavily snow dominated see probably the least amount of benefit from soil moisture. But as you move down slope to more transitional elevations, and particularly some of these larger river basins where they have both sort of rain dominated and snow dominated, like the Missouri River Basin, the upper Missouri, you tend to see more and more, and sometimes actually soil moisture itself is more skillful than snowpack. I think it would be helpful though, yeah, to put some numbers on those. And I could probably dig that up for you another time. But yeah, I would say that in general, it's more for these transitional and rain dominated places where we see it.
Great, thank you. Let's see, we've got another question. This is something I've never thought about, and I don't know if either of you have thought about it. I bet one of you has. And the question is this: if temperatures are generally warmer while snowpack is present during colder months, does that cause water to be stored in a different form, like ice created from melting and then freezing? If so, how does that impact the snow season and melt rate in the spring? I wondered if climate change could actually result in changes to persistence of the snowpack if it's in ice form. Are either of you aware of any research related to, changes in behavior of snowpack and ice and melt?
I'm not sure I completely understand the question.
Okay.
If
Yeah.
if I can paraphrase the question, it may be associated with if there's an increase in melt, for example, but the water remains in the system, like for example in the soil, then does that have an appreciable, like what is the effect of the fact that the water is still stored within the system? And that may not be an accurate paraphrasing of the question, but I'll answer it anyway, which is that we're actually engaged in a lot of research right now that is aimed at understanding how snowmelt is partitioned between evapotranspiration and streamflow as a function of the timing of snowmelt. And so potential evapotranspiration is very much seasonal and increases as you move toward the summer period. And so if snowmelt occurs at a time period when potential evapotranspiration is relatively low, and more of that water will be partitioned to streamflow and less to evapotranspiration. So this shift in the timing of snowmelt, even if the total quantity of water moving into the system is the same, if you shift the water input in time toward a period of time when potential evapotranspiration is relatively low, then you may actually partition more of that snowmelt into streamflow than would otherwise be the case. And so the devil's in the details with this, and it's obviously quite complex. And the degree to which vegetation responds to that water availability influences that partitioning as well as how water is stored within the soil. So it actually requires a holistic look at watersheds in a way that leverages hydrologic science, atmospheric sciences, ecological sciences, and soil science. So it's a pretty complex interconnected system, obviously.
Absolutely. Yeah, it's such a complicated system. Thank you for tackling that one, Noah. I've got a question that I think applies to both of you, and that is, are you considering the effects of wildfire as a factor in the reliability and accuracy of predictions? And then they also mentioned dust deposition, and I saw dust on snow in a separate question. So maybe we could talk about both of those things, dust on snow, if either of you is looking at that or considering that, and then also wildfire impacts on snow and stream flow prediction.
Hey, thanks, Benay. Maybe I'll take the first part of that, the dust on snow part, and say, in the work that we did where Noah and I were collaborating, we actually also considered the role of dust together with forest disturbance. And we did find that dust was fairly conclusively causing earlier snowmelt, but the volume, the change in total like water yield was not very clear. And we actually got some conflicting results depending on the method that we used. So I would put sort of an asterisk next to any sort of estimates of changes in water yield, at least from my perspective. In terms of forest fire, I have worked primarily with bark beetle disturbance. I think that anytime we're working with remote sensing, and probably in Noah's work specifically, and he can speak to this, the change in the forest structure, canopy structure is going to be seen in those remote sensing products. So maybe that's a good sort of transition comment.
Yeah, I mean, I can add that the dynamic models and data layers that we use in our methods are sensitive to changes in forest cover, but that requires that we're updating, for example, the vegetation layers on a frequent enough basis that the most recent fires are included in that record. And so we often are lagging behind the most recent forest cover disturbances because we can't really keep up with the rate of land cover change in terms of updating our vegetation layers and then rerunning all of the historical SWE reanalyses as the case may be to honor the fact that that land cover change may have occurred during that time period. But it's something we're aware of, and it does have a profound impact, obviously, on the snow dynamics. So we aim to represent it as best we can.
Perfect. Thank you, Noah. Thank you, Ben. Let's see, we've got another question here. I think this is directed towards Ben, but I think it might apply to both of you. So the question is, for the Front Range, last year's actual stream flow was much lower than the forecasted stream flow. So could you please describe how your work could help with this concern? And maybe you could talk a little bit also about why there was that difference between forecasted stream flow and actual stream flow.
Yeah, well, so no, that's a great question. And that really ties to like the second part of my talk where we look at the future, and it's this exact type of thing that is what we're seeing in the mid and late century, where you have a roughly average snowpack. So you're not anticipating a drought, but then the spring is dry and the summer is dry and you actually experience a drought. And so it's this exact thing that we're dealing with. So there's sort of two factors to it. One is like, what do we know on April 1st, let's say? Well, we know the snowpack and we know some other things, and we're using some, but probably not all of the things that we know. And then there's just the random nature of the climate, which means after you make that prediction on April 1st, any number of things can happen. And so the part that we have more control over, I would say, is the things that we know when we issue the forecast. And so my sort of feeling is that it would be most sort of beneficial to focus on expanding our inventory of environmental variables at the date of the forecast issue, and that, you know, slow progress will be made on seasonal weather forecasting. And so that would be my comment to that.
Yeah, I would just add, I mean, Ben's more of the expert on this, but last spring, really across the Western United States in the month of April was seeing snow melt rates that were much higher than on average for the month of April. And so, you know, conceptualizing that, snow melt rates tend to increase as we move later into the melt season. So April is not, you know, obviously there's a lot of melt occurring in April, but as a rate, there's less energy available for driving melt in April than in May or in June. And last April, there was a quite anomalously high melt rates, and the system was drying out much faster than normal. Here on the Front Range, normally April and May are relatively wet months. And that wasn't really the case for April of last year. And so I think that the quantity of water moving into the system was altered by that. And in a probabilistic forecast sense, as kind of what Ben was alluding to, you're gonna over predict stream flow if you're expecting an average amount of precipitation to occur in April and in May. And then if it doesn't occur, combined with that, if we have a lot more melt occurring in those earlier months, then we may have differences in the amount of that snow melt that's partitioned to stream flow than normal. And if it's shifting in time, then that can impact how much ends up as stream flow as well.
Fantastic. Thank you so much, both of you. And I just realized I meant to be sharing this one last little slide that has our contact information. So I'm going to show that now as we wrap up. It looks like we are just about out of time today, but I want to thank everybody so much for joining today's webinar and their wonderful questions. And I'd like to thank Noah and Ben for their presentations and for answering all of your wonderful questions. If we didn't get to your questions today, we will take a look at them, but please feel free to follow up with us. Our email addresses are on this slide. So if you asked a question and it didn't get answered, feel free to reach out and we can try to get some answers for you. And just as a reminder, we will be posting a recording of this webinar on our website, and we will send you all the link when it's posted. And yeah, please feel free to reach out to us if you want to keep the conversation going. So with that, have a wonderful afternoon and happy Friday, everyone. Thank you.